Hello guys, welcome to our channel. So today we are going to be looking at a problem in the Northwest Mock 2020 projectile motion. That is advanced level maths paper number 3, which is normally called maths mechanics. So let's dive right into the question. It says a particle is projected from a point on a horizontal plane with speed v meters per second at an angle theta above the plane. Show that the time the particle takes to reach the maximum height above the plane of projection is v sine theta on g. The B part of the question says that a particle P1 is fired from the origin O with speed U1 at an angle of inclination alpha above the x-axis, which is horizontal. At the instant where P1 is at the highest point of its path, second particle P2 is fired from O with U2 at an angle of inclination beta above the horizontal, such that the two particles collide on a point at the x-axis. Show that 4 tan beta equals tan alpha. All right, so Alright guys, so let's look at the solution to the problem. So a particle is projected from a point on the horizontal plane with speed that at an angle that above the plane. Show that the time the particle takes to reach the maximum height above the plane. Alright, so this problem is a proof. So what we really want to do in projectile motion is actually try to represent the particular motion on a diagram so that you can really analyze what is happening. So this is my little diagram I've drawn here. So we have this particle projected with the speed v at an angle theta from the horizontal, and then of course we can resolve this speed into the vertical and horizontal components. Again, this is something that I've always emphasized. Every single thing that is a vector quantity in projectile motion should be resolved into the vertical and horizontal components, because again, projectile motion, you are basically studying the equation, you are studying the motion of a particular particle in two planes. Really, that's what it is. So every single one of those equations of motion which we study in normal mechanics is still applicable in projectile motion, but the problem is, or the little difference is, that you're applying those equations of motions in planes. So you have to be precise. Which plane are you applying a particular equation of motion to? All right, so let's solve the problem. We use this equation of motion v equals to u plus at. All right, so now we want to apply this equation of motion in planes, because we are talking about the time it takes to reach this maximum height. You realize that we're already talking about the motion of this particle in the vertical plane. So we have our vy uy minus gt, because our acceleration there in the vertical plane is just g. Of course, acceleration in the horizontal plane does not exist, because acceleration due to gravity is just, acts vertically downwards and not horizontally, right? So good. So in this vertical plane, we are now going to say that our time of flight is basically uy minus vy on g. So we've made time of flight the subject, and then our uy here, we just resolve this velocity in the vertical plane, right? So if you resolve this velocity in the vertical plane, what are you going to have? We are going to have v sine theta. This is v sine theta here. This is a vertical plane here. So opposite to this angle will be sine theta. So we have our v sine theta there for the initial velocity. And then the final velocity at this maximum point like that. Remember that at this maximum point of every projectile, the projectile has just the horizontal component of velocity. So it does no longer rise. So at this particular point like that, the vertical component of the velocity is 0. Right? That's why it curves downward. It goes horizontally, and then it starts curving back downward as a result of gravity. So that final vertical velocity at that maximum height is simply 0. So we have t to be equals to our uy, which is basically this v sine theta here over g, since this guy is 0. So again, you realize that this is simply the proof, right? You've just applied this basic equation of motion and then applied it in the plane of the projectile, and then you've simply gotten the proof. So you had to do that for 3 marks. All right, so let's go on to the next part of the question. All right, so the next part of our question is this question. So you can just pause it a bit and then read the problem. I'll just delve right into solving it. So we want to really draw a diagram for every projectile question we have. You have to draw that diagram. So this h is not supposed to be here. I'll just wipe it off. All right, so forget about this one. So this is the h here, which is simply the maximum point on this projectile path. Right? So you realize that P2 is projected when P1 is at its maximum point, and then P1 and P2 still eventually collide at this point where I've just, these scribbles, I've just made these small scribbles. So the two of them still collide at this point. You realize that if P2 is projected when P1 is already at H, therefore the time taken for P1 to move from H all the way to this point where they collide is simply equal to the time of flight of P2, right? Perfect. So we are just going to go ahead and analyze the time of flight of P1 first. We want to look at the motion of P1 first because we have its angle, we have its initial velocity, it's projected. So we can look at its time of flight to be 2u1 sine alpha over g. Again, the first part of the question said it should show that the time taken for a projectile particle to get to this h is u1 sine alpha on g. So the time taken for it to get to this h and all the way back to this point on the same horizontal plane will simply be 2 times the time it takes to get to that point, because h is simply, you know, this particular projectile path is symmetrical about h. Perfect. So we want to go ahead and then analyze the motion now of P2, since we already know the time of flight of P1. Now the time of flight of P2, normally you can come over here. So you can come over here and then look at that and realize that the time of flight of T2 would simply again use the same equation, 2u2 sine beta over g. Again, you are using u2 because the particle is projected with the speed u2 instead of u1 now, and then you are using beta because its own angle it makes with the horizontal is beta instead of alpha. So you use the same things, changing the parameters for that particular projectile, and then it gives you the same time of flight. But you realize that this time of flight like that is basically the time for P1 to move from H all the way down here, which is the same time P1 would take to move from O here all the way to H. So you realize that the time of flight of P2 is simply u1 sine alpha on g. That is very, very important. Now you can use this relationship like this between their time of flight, and then you get an expression. So you realize that if I equate these two things together, this g would cancel with this g, and then you realize that our u1 sine alpha, which is this over here, would simply be 2u2 sine beta. So we want to form equation 1 there, and then we go over to analyzing the next part of the question, which is talking about the two particles colliding at a particular point here. So I want to call this point from O, all the way from O all the way to this point, to be x. So you realize that the horizontal displacement covered by the two particles P1 and P2 is simply equal at the point where they collide. Alright, so at point of collision, x1 is equals to x2. Perfect. So again, we want to get the x1 and x2 for these various projectile particles. So what we really want to do, again, projectiles is just using you are just applying the equations of motion, right, in the planes to which you want to study the motion of that particle, really. So we are going to use this equation of motion S because we want to study the horizontal displacement of the particle, or the horizontal distance covered by each of those particles all the way to this point where they collide. So again, you are going to be realizing that we're analyzing that motion in the horizontal plane in the x direction. So we're going to be talking about Sx. So that's why I said Sx here will be equals to ux times t minus half at squared. But then since acceleration in the horizontal plane does not exist, this term is just 0. So we have our Sx to be ux times t. So you realize that our Sx, we'll just call it x1 for particle 1. So the horizontal distance for particle 1 is just x1. Then in place of our ux, remember that our ux is you have to resolve this velocity in the horizontal direction. It will just be u1 cos alpha. So our ux is u1 cos alpha, and then times t, which is the time of flight of this particle, because it's the time for it to leave from O all the way to the point where they collide. So you want to call that time t1 for P1. So x1 will be equals to u1 t1 cos alpha. So that's the horizontal distance covered by P1. Then you want to go ahead and introduce what t1 is. So our t1 from here is 2u1 sine alpha on g. So you simply put that 2u1 sine alpha on g where you see t1, and then you simplify. You realize that we'll have x1 to be 2u1 squared sine alpha cos alpha on g. So we want to go over and get x2. So to get x2, again, remember that our x1 was just u1 t1 cos alpha. So our x2 now will simply be u2 t2 cos beta, because the particle t2 was projected, p2 was projected with a velocity u2. Its own time of flight will be t2, and then at an angle of projection from the horizontal plane beta. So we want to just use those parameters and then get its own time, its own horizontal distance like that. So if you put in t2 there, so our t2 again is simply this 2u2 sine beta over g. So you want to take this guy and then put in here where you see t2, and then you simplify, you would have this. So again, x1 equals x2 at this point where they collide. So you can basically realize that I'll be equating this x2 to this x1. So if I take these two guys and I equate, I have this expression coming out. So if I simplify that out, I can simply make my u1 the subject, because these two here will cancel with these two, this g cancels with this g. So my u1 squared will simply be all of these things divided by sine alpha cos alpha, which is this. So we want to call that one equation 2. Now we have equation 1 here, and then we have equation 2 here. Now, but from our equation 1, you realize that we can make u1 the subject here, which is just, if you come over here and to make u1 the subject, you have 2u2 sine beta over sine alpha. So you want to come over here and then you make that u1 like that. So in the place of this, our u1, we'll simply put all of these things and then we square it. So you are taking, you make u1 the subject in equation 1 and then you substitute in equation 2. So if you substitute u1 in equation 2, you have this, all that squared equals this. So you want to square and then simplify. So if you square, you would have 4u2 squared sine squared beta, all that over sine squared alpha equals to all of this. So if you cross multiply, so you would have something like this. This sine alpha would cancel one of these sine alphas, and then you'll be left with sine alpha over cos alpha, which gives you tan alpha. Then you're left with all of this term on above. So you have this thing. Again, you want to make tan alpha the subject. So yeah, I want to make tan alpha the subject because the proof says that 4 tan beta equals tan alpha. So if I can make tan alpha the subject, whatever I have left, I'll just simplify until I get this guy. Okay, so let's make tan alpha the subject. I've made tan alpha the subject. I divide all through by this thing, so I have this. So we can simplify this expression. This are sine beta. We'll cancel one of the sine betas. We are left with sine beta over cos beta. Sine beta over cos beta is tan beta. So you basically left with 4 tan beta. So our tan alpha is equals to 4 tan beta. So you realize that that is the proof, and that is it. So you have all your 13 marks for getting that. Thank you so much.